Today I would like to discuss some ideas around how to estimate generalization ability of generative models. First of all, a few words about generative modeling. Nowadays, generative modeling is a very well-developed domain of neural networks. It allows to represent complex images. Currently you can even generate images and other complex types of data controlled by, for example, textual description. The simplest structure of a generative model, it is a special classes of neural networks. Neural networks are actually a special functional classes with a lot of parameters. These parameters are tuned by some stochastic gradient descent algorithms based on empirical samples. So this neural network takes as input some IID random noise with a simple distribution, a low-dimensional vector of random noise, and transform it to a more complex distribution, living in a high-dimensional space, for example, of real images. And currently, the quality of these images that it can generate is very high. However, most of approaches to train such systems is quite heuristic. And the question is how to estimate the generalization ability, accuracy of representing distributions of true data. Before formulating the main problem and the main results, first let me present several background results around optimal transport. First of all, in order to formulate formally in a mathematically rigorous way the problem of generative modeling, we can consider so-called optimal transport problem. We have two distributions, P and Q. For example, P can be a distribution of noise, and Q can be a distribution of real images. And we would like to construct the transformation T, which maps one distribution P, distribution of noise, exactly to the distribution of images Q. And we, among all possible such transformations, we would like to find such transformation T, which is close to identity as possible. In other words, we minimize this integral with respect to all possible measurable transformations T. This is a very well-known result that such cost function is equivalent. So this is the semi-dual problem. In order to calculate the value of the cost function, we can also solve the semi-dual problem, that is optimized with respect to all possible continuous measurable functions f. This integral with respect to this sum of these two integrals with respect to distributions p and q. And fc is a c conjugate of the function f. F is called usually potential. And this is also a very well-known result from the theory of optimal transport. This result states that if f star is the optimal potential, optimal with respect to this optimization problem, then it has the following structure. It is just a difference between the squared argument minus phi star, and phi star here is the convex optimal potential. And so instead of solving this semi-dual problem, we can slightly simplify it. And actually, we should just solve this optimization problem by optimizing all possible potentials phi, where phi with dash here is the conjugate function. What is important is that it also can be proved that phi here should be a convex function. So it is even more a more restricted class of functions. So in other words, in order to solve the optimal transport problem, we should find such convex function phi, which minimizes this functional, where phi with dash is the conjugate, and it can be also proved if we find the optimal solution of this optimal transport problem, then the gradient of this function is exactly the optimal transport map, which exactly maps the distribution P to distribution Q. What is the problem we would like to solve? In practice, we don't have, of course, any information about the distribution P and distribution Q. In practice, we only have some sample of points generated randomly IID from distribution P, and also the sample of points generated randomly IID from distribution Q. These are multidimensional samples of multidimensional vectors, and we would like, based on these two samples, to solve the optimal transport problem, to construct such nonlinear transformation, which as close as possible to the true transformation, and also it can be used to map any new point x generated from distribution P to some points such that this point is generated as if this point is generated from distribution Q. In other words, in practice, instead of solving this optimization problem, because we cannot calculate these integrals, we solve this optimization problem. So we estimate these integrals by Monte Carlo. And of course, in practice, we cannot optimize with respect to all possible convex functions. So we take even more narrow class of functions. In practice, usually we consider convex neural networks, input convex neural networks. This is a class of neural networks which are convex. So these are just convex functions, and they are convenient in terms of various computational algorithms. And so in practice, to solve the optimal transport problem, we optimize this empirical functional. And our hope is that when we find the solution of this functional, when we find the solution of this optimization problem, it will be close in some sense to solution of this problem. And so the question is how to estimate this error. Here, theta is the vector of parameters of the neural network. So usually neural networks have many parameters. One of the difficulties with such empirical formulation is that here we have this conjugate function phi. In practice, numerically, it's not possible to estimate conjugate function for any function phi, because function phi is a very complex function with some high dimensional argument. So even numerically, it's too difficult. And so this empirical optimization problem cannot be solved. And in order to solve it in practice, we use the following trick. Let's consider this term here, the first term. Actually, this conjugate function phi with dash here, it is actually the maximum over all possible y of this expression. So for all possible x, for each x, we should find argmax of this expression. We can prove, it's actually a very simple technical statement, that instead of finding for each x the corresponding argmax y, we can, instead of this, we can take the maximum with respect to all possible measurable transformations t, which maps each x to the corresponding argmax y. And so it means that instead of solving this minimization problem with phi which is conjugate to phi here, we should solve this min-max optimization problem where phi is belongs to a set of convex functions and t is just a measurable map. And from practical point of view, this is easier. And in my further discussion, I will consider only this optimization formulation of the optimization problem. Also, by construction, and again, it's a very simple technical statement to prove, this optimal T solution of this optimal of this minimax problem will be exactly the optimal transport map, which maps distribution P to distribution Q. And so finally, this is the theoretical problem we are going to solve, we are going to discuss in the second part of my talk. So as I said, we don't have exact expressions for this distribution P and distribution Q. These are some high-dimensional distributions. And moreover, in practice, distribution Q is a distribution of real-world images, so it's even not possible to have any representation of it. The only thing we have is the are samples from these distributions. So say samples of noise from distribution P and a sample of real-world images which we just randomly collected from the internet, as if they were generated by some distribution Q. And in practice, instead of this optimization problem, we solve this empirical optimization problem. So we restrict our map T to some class of neural networks, because it's from a computational point of view, it's very convenient. And so now class of functions T is parameterized by some vector of parameters theta, and phi we also take as a neural network which is input convex, and we parameterize it by some vector of parameters omega. We, instead of calculating integrals, we just estimate them by Monte Carlo. And so we minimize with respect to theta, maximize with respect to omega. And after we obtain the solution of this min-max optimization, we get some empirical map T hat. And the question is, to what extent this T hat is close to the true optimal transport map? Here, the expectation is taken with respect to the realizations of the samples from distribution P and distribution Q. And so this is what we want to estimate. So now let's discuss theoretical results. As I said, this is the empirical loss function which we minimize and maximize, L hat. And let's denote by phi hat is the arg minimum of this expression. Here maximum is taken with respect to some restricted class of functions, not with respect to all possible measurable functions, but only with respect to the restricted class of functions. In our case, this is the class of neural networks. And this is some other restricted class of functions, also a class of input convex neural networks. And by T hat, we denote this argmax of this empirical function, where we put as the first argument the empirical potential phi hat. By R capital here, I just denote that we take maximum and minimum with respect to the restricted function classes. And so our aim is to estimate this generalization error. First of all, in order to do this, we first of all need to introduce these errors. So these are different types of errors. We call it like outer approximation error here. As you see, the main difference between these two terms is only here. I just take the minimum with respect to the restricted class of functions phi. Here, it's inner approximation error. The main difference between these two terms is here that the class of functions for t is restricted. It is some class of neural networks. And also we have two types of empirical errors, outer estimation error and then inner estimation error expectation. And here I just put the empirical phi hat, which is the solution of this optimization problem. Here is it. And I take the difference between these two terms when I take minimum with respect to phi, with respect to all possible phi. And the same is inner approximation error. So you see that I just put as two arguments to this function L or both to empirical estimates. And here is the first result. So we can bound the difference between the true optimal transport map and its approximation, which we obtained by solving that empirical optimization, as follows. Here, unfortunately, we need to impose some additional technical constraint that the class of neural networks which we use to model the function phi, it should be a class not only of just convex neural networks, input convex neural networks, but it should be also beta strongly convex functions. So it means that there should be some additional term which behaves quadratically. Beta can be very small, but still technically it is required. This is the first result. Now we should bound all the terms in this expression. To do this, first of all, we bound the empirical error. The empirical, both of empirical errors, their sum, can be bounded by this expression. And this is quite typical result for learning theory. This result means that the empirical error is bounded by two Rademacher complexities. This is the Rademacher complexity of the function class phi, which is phi capital, which is used to model convex potentials. It's a Rademacher complexity with respect to the distribution Q and sample size M. And this is a Rademacher complexity with respect to function of the function class H capital, which is actually all possible functions H, which can be represented in this way. This is how we can bound the empirical errors. And now a few words about how we can bound approximation errors. First of all, we can prove, again, these are quite maybe not explicit approximation results, but at least they guarantee that if we take a neural network with sufficient number of layers, with sufficient number of neurons, so which means the function class has high capacity. So if we do this, then we can make the approximation error arbitrarily small. In other words, the inner approximation error can be for any predefined epsilon. We can find such such class of neural networks tau capital, which such that the inner approximation error is smaller than epsilon, and we can prove that as such class tau capital, we can use special neural networks, which are very widely used in practice, so-called multi-layer perceptron with rectified linear units as neurons. Moreover, in this theorem, as a class of functions phi capital for modeling these potentials phi, we can use beta strongly input convex neural networks, and these neural networks has such form. Phi is just the input convex neural network plus we add some small addition which guarantees that this function class contains beta convex, strongly convex functions. And the same we can prove for these classes of neural networks. The same we can prove for outer approximation error. In other words, there exists a class of Lipschitz beta strongly convex functions, totally bounded with respect to the Lipschitz norm, such the outer approximation error, which depends on the class of functions phi, this class of functions, this outer approximation error is smaller than epsilon. The only technical requirement here, and unfortunately still we cannot avoid it, is that we assume that the optimal potential phi star is not only just convex, which is required by the optimal transport theory, it should be also beta strongly convex. This is a limitation of these results, but still this is what we have up to now. Finally, by combining all these estimates, we can prove that the expectation of this error between the true optimal transport map, which maps random noise into, say, distribution of images, and its empirical version. This is the true optimal transport map, which we don't know, of course. And we obtain by solving the empirical optimization problem with respect to classes of with respect to function classes of neural networks, we obtain the its empirical the empirical optimal transport map, and this error is upper bounded by the approximation error epsilon plus this empirical term, which is upper bounded by Rademacher complexities. And we can prove easily that for the classes of neural networks we consider here, I mean this class of neural networks and this class of neural networks, these Rademacher complexities are upper bounded by, with respect to sample sizes, n is a sample size from distribution P, sample from distribution P, and m is the sample size sample from the distribution Q. And so this is upper bounded in this way. Of course, these terms here, they depend on dimensionalities, but this, I don't want to say that these errors are really kind of, these estimates are really sharp. These are first results of this type. And we also checked empirically that empirical error we observe in practice when we know the optimal transport map. In some very simple cases of distributions, we can obtain optimal transport map explicitly. So these are empirical errors, and this is the slope from this upper bound. So that's it. And actually, we have many papers about how we can use theory of optimal transport to analyze properties and make algorithms of generative modeling efficient. And this is one of the theoretical papers which we developed to justify how it works and what error we can get. That's it. Thank you.
Yeah, let's thank you.